Hello everyone, welcome to this lecture. So, in this lecture we will discuss about interactive protocols, namely our focus till now was on solving the problem of secure communication where we had two entities, a sender and a receiver, and we extensively discussed how to design algorithms to solve the problem of secure communication. But now what we are going to discuss is a scenario, is a well known problem where we have multiple entities and our goal is to design a cryptographic protocol which requires interaction among the entities. So, specifically the roadmap for this lecture is as follows. We will introduce the problem of secret sharing, we will see additive secret sharing, replicated secret sharing, and then we will see the classic construction of secret sharing scheme due to Adi Shamir. So, let us see the motivation of secret sharing. So, imagine we have a banking application say where the locker in the bank it is accessible only by the managers in the following way. The password for the locker is shared among the 3 managers and it is shared in such a way that if only 2 of the managers go together and enter their respective password, the lockers can be accessed, but if only a single manager tries to enter the password and access the locker, the access is not possible, right. So, for instance, if the second manager goes and tries to open the locker, it should not be able to do that. In the same way, if the third manager go, it should fail, but if we take any set of 2 or more number of managers and they go and enter their respective passwords, they should be able to access the locker. So, that is what we require here. Okay. In the same way, consider another real world scenario. This is a real world scenario which really happened during 90s. So, this is regarding how the Russia's nuclear weapon was accessible by the top leaders of the country. So, it is believed that the password to launch the Russia's nuclear weapon, it was shared between top 3 entities of the country, namely the president, prime minister and defense minister, in such a way that the weapon could be accessed or launched only if at least 2 of the 3 entities come together and enter their password. Whereas, if only a single entity tried to launch or access the weapon, the access will be denied. So, both these applications can be abstracted by the following problem, which we call as n comma t secret sharing, and this problem was independently formulated by Shamir in 1979 and Blackley in 1979. So, what we are given here is we are given the following setting. We have a set of n parties P1 to Pn and they are connected by pairwise private and authentic channel. What it means is, if any information Pi wants to send it to Pj, we assume that it has a dedicated channel with which it is connected to Pj, and anything Pi sends over that channel to Pj, which it will be received correctly and securely by Pj. If you are wondering how exactly that such channels are available in real world, well, we can use any of the well known secure communication protocol that we have extensively discussed till now to ensure that such channels are available between every pair of parties. Now, apart from these n parties, we have a designated party among those n parties and everyone will know the identity of that party, and it is called as dealer, and dealer has some private input, a secret little s from a bigger space, which is the set of all possible secrets. Now, the goal of this dealer is to distribute its secret among the n parties by coming up or computing a share Si for each of the party and giving a share to each of these parties. So, the first shareholder of party 1 gets a share S1, second party should get a second share, the nth party should get the nth share, and these shares are distributed over the pairwise channel with which dealer is connected to the individual shareholders. Now, we require the following properties from this distribution of shares. We require that it should be impossible for any set of t or less number of shareholders to exchange their shares and reconstruct back the secret S. And depending upon whether the set of t shareholders who are trying to reconstruct back the secret, whether they are computationally bounded or they are computationally unbounded, we achieve either perfect secrecy or computational secrecy. So, that is the first requirement from this distribution of shares. On the other hand, if any set of t plus 1 or more shareholders pool together their shares, then it should be possible to reconstruct back the secret S. So, the parameter t here is acting as a threshold for you. That means, we require a sharing mechanism such that if any set of t or less number of shareholders they come together, they should fail to access or they should fail to reconstruct the secret. the share should be completely independent of the underlying secret. On the other hand, if any set of t plus 1 or more number of shareholders come together, the secret should be reconstructed. It should be possible to reconstruct back the secret. So, let us see a very simple construction of an n comma n minus 1 additive secret sharing scheme. So, basically here my threshold is t, that means I require a sharing mechanism where all the n shareholders should come together to reconstruct back the secret, but if any single shareholder is missing, then the secret should not be, it should not be possible to reconstruct back the secret. And why it is called additive secret sharing, it should be clear to you very soon. So, here my secret space is a set of all possible L bit strings, and as I said, my threshold t is equal to n minus 1. The sharing algorithm is as follows. So, imagine dealer has a secret S consisting of little L bits. To share it, it picks n minus 1 shares randomly from the set of L bit strings. That means, the first share is a random L bit string, the second share is a random L bit string, and in the same way the n minus share is also a random L bit string. Now, once the first n minus 1 shares are fixed by the dealer, the nth share is computed to be the XOR of the first n minus share and the secret S. And once the n shares are computed, the dealer sends the respective shares to the respective shareholders. Namely, the ith share Si is given to the party Pi over the dedicated, secure and authentic channel between the dealer and the ith party. So, the correctness property here is trivial for this secret sharing, namely if all the n shareholders come together and exchange their shares with each other, then indeed they can perform the XOR of all the n shares and they will uniquely get back the underlying secret S which was shared by the dealer. Now, let us formally prove the privacy property here. So, for privacy, our goal is to show that if among these n shareholders any n minus 1 shareholders come together and pool their shares, they should not learn anything about the underlying secret S. So, we divide the proof into two cases. So, consider the case when the set of n minus 1 shareholders who are corrupted and they are trying to reconstruct the secret are the first n minus 1 shareholders. It turns out that if the first n minus 1 shareholders are corrupt, then from their shares they learn absolutely nothing about the underlying secret S, because if you see the sharing algorithm, the first n minus 1 shares they are picked independently of the actual secret of the dealer. So, that means if the adversary controls the first n minus 1 shareholders and access their shares, the adversary learns absolutely nothing about the dealer's secret. That is case 1. On the other hand, consider the case when the set of n minus 1 shareholders definitely includes the nth shareholder, because the nth shareholder, its share is a function of the secret S and the remaining n minus 1 shares. So, the second case is when the collision of n minus 1 shareholders excludes some party Pj, where Pj is definitely different from the nth party. That means, the nth party is definitely in the collision here. So, for simplicity you can imagine that my Pj is equal to P1. That means, the adversary is corrupting the last n minus 1 shareholders here. It turns out that the missing share which the set of n minus 1 shareholders are missing in this example, the share S1, that is independent of the secret S, because that was picked randomly by the dealer. And that ensures that even though the nth shareholders learns Sn, which is computed as the XOR of the actual secret of the dealer and the remaining n minus 1 shareholders, it ensures that the nth share is also independent of the secret S. Because for instance, if we are considering the case say where P1 is missing in the collision, then from the viewpoint of the attacker knows that the value of Sn which it has learnt is equal to some unknown secret S. So, I am putting this S in the box here to show signify that it is unknown to the attacker, and even the first share is also not known to the attacker here, because I am considering the case where all but the first party is under the control of the adversary, but rest of the values is known to the attacker, unknown to the attacker, right. So, more or less we are exactly in the same situation as we were in the one time pad scheme. So, you can imagine that this S of n is nothing but a one time pad encryption of the message S with a key, where the key is nothing but the XOR of the last n minus 1 pieces which are known to the adversary plus some random value S1 which is not known to the attacker. That means, even though adversary is seeing S of n, it cannot figure out whether S of n is actually a share corresponding to the secret S or corresponding to a secret S prime, because it does not know the value of the missing share S1, which was randomly picked and independently picked, which was randomly picked and independent of the actual secret of the dealer. That ensures that even if the adversary controls the nth shareholder, it learns absolutely nothing about the underlying secret S, and that is why this secret sharing satisfies the requirement of an n comma n minus 1 secret sharing scheme. So, it turns out that the additive secret sharing that we have discussed, it works only if my threshold is n minus 1. But in general, I might be interested to design a secret sharing scheme where my threshold need not be n minus 1. My threshold could be strictly less than n minus 1. So, now let us see a solution, a naive solution of coming up with a secret sharing scheme for any threshold t which is less than n minus 1. So, the idea here is we take every proper subset of the set of n parties say T, say big T, where the size of big T is T plus 1. So, we take every possible subset of size T plus 1 of the n parties and run a dedicated and independent instance of additive secret sharing among that subset of T plus 1 parties as the shareholders, with the threshold being T plus 1. And the idea here is that if we do this for every subset of size T plus 1, then when it comes to the actual collision of T shareholders who might try to learn about the secret, that collision of T shareholders will miss at least one share to reconstruct back the actual shared secret. So, what I am trying to say is, let us demonstrate it by this example. So, imagine my n is equal to 4 and I want to design a scheme where my threshold T should be 2. That means, any subset of 3 shareholders should be able to reconstruct back the secret, but any set of 2 shareholders, if they try to pool their share, they should fail to reconstruct back the secret. So, the idea here is that the dealer treats this set of 4 parties into different subsets of size 3 parties. So, say T1 is the first subset, T2 is the first subset, and like that we have the fourth subset T4. Now, in the first subset, dealer consider P1, P2, P3 to be the shareholders, and it runs an instance of an additive secret sharing scheme with the threshold being T equal to 2, but considering only the parties P1, P2, P3 to be the shareholders. Namely, dealer picks random shares S of 1 1, S of 1 2, S of 1 3 such that their sum is equal to the secret S, and the say shares are given to the respective shareholders P1, P2, P3. Independently, dealer runs another instance of additive secret sharing for the same secret S and picks or computes 3 shares such that their sum is equal to the secret S, and the respective shares are given to P1, P2, P4 who are the shareholders in this second subset T2. In the same way, dealer creates another instance of the additive secret sharing for the subset T3 and another instance of additive secret sharing for the shareholders in the set T4. Now, what is the total share for the party P1? The total share of the party P1 is all the shares which it is getting from the respective subsets in which it is present. So, the share of P1 will be the piece S11 because it is present in the subset T1, as well as the piece S21 because it is present in the set T2, and these will be the total shares for the party P1. In the same way, the share for P2 will be S12, S22 and so on, and S41 and so on. So, in fact, the share of P1 will be S31 as well because P1 is also present in the third subset. And now, it is easy to see that irrespective of which 2 parties get corrupt, because my threshold T is equal to 2, those 2 shareholders learn absolutely no information about the secret S. So, for instance, if P1 and P2 gets corrupt, they are under the control of the adversary, then based on their shares that they learn due to their presence in the subset T1, P1 and P2 fails to learn the secret S because the share S13 is missing for P1 comma P2. In the same way, with respect to the subset T2, P1 and P2 are missing the share S23, and that is why the secret S will not be known to P1, P2 and so on. So, it does not matter which subset of T parties get corrupt, based on their shares they fail to learn the actual secret S. So, now you might be wondering that we now have a secret sharing scheme for any threshold t with respect to the value of n, but it turns out that this scheme is inefficient because the number of subsets of size t plus 1 is n choose t plus 1, which becomes an exponential quantity if t is approximately n over 2. That means, dealer basically has to deal with exponential number of values here, and same is the case for every shareholder. So, this is an inefficient solution, and let us now discuss a very clever solution for n comma t secret sharing due to Shamir, and this is one of the simplest cryptographic constructions that you can think of. This is my personal favorite, and this is based on simple arithmetic which you might have learned during your high school. So, the idea here is if you want to share a secret S, then to share it you pick a random polynomial f of x of degree t such that the constant term of the secret, a constant term of the polynomial is the secret which you want to share, and let the shares be distinct points or the values lying on that polynomial. So, to demonstrate my point, imagine my threshold t is equal to 1 and I have a secret S, I am the dealer. What I can do is to share the secret S, since my threshold t is equal to 1, I pick a random straight line, it could be any straight line in the plane, with the only restriction being that its constant term should be the secret S which I want to share. And what I can now do is I can evaluate or I can compute the value of this straight line at some fixed publicly known distinct values, say at x equal to alpha 1, at x equal to alpha 2 and x equal to alpha 3, and these are the shares for the first party, second party and third party respectively. That means, the first party will have the share S1, the second party will have the share S2 and the third party will have the share S3. It will be publicly known to everyone that the first party is obtaining the value of the straight line that dealer has picked at x equal to alpha 1. So, these alpha values, they are publicly known, and it's everyone knows that alpha 1 is associated with the first party, alpha 2 is associated with the second party and so on. Right. So, that is a Shamir's secret sharing scheme. Now, let us try to prove that why intuitively it satisfies the requirement of n comma t secret sharing. So, it is easy to see that if t plus 1 shareholders come together, then they can uniquely reconstruct back the t degree polynomial which dealer has picked, because t plus 1 distinct values on an unknown t degree polynomial suffice to uniquely reconstruct back that polynomial. So, for example, if t is equal to 1 and say the first two shareholders comes up with their shares S1 and S2, then they can uniquely find the straight line passing through the points alpha 1 comma S1 and alpha 2 comma S2 by fitting a straight line equation. Once they obtain the straight line, they can take the constant term of that straight line, namely S, to be the recovered secret. On the other hand, the second fact that we can use for polynomials of degree t is that if we take any t shareholders who are the bad guys and they are trying to reconstruct back the dealer's secret, they will fail to do that, because t distinct values does not suffice to uniquely recover back the unknown t degree polynomial f of x which was picked by the dealer. More specifically, in this example, since t is equal to 1, say the first shareholder is corrupt, then from its viewpoint there could be infinite number of straight lines possible in the plane passing through his point alpha 1 comma S1. That means, it could be the case that dealer might have picked this blue straight line, giving the first shareholder the share S1. In that case, from the viewpoint of the first shareholder, it could be the case that S double prime is the secret, or it might be the case that this red line is the straight line which dealer might have picked, such that that straight line when evaluated at alpha 1 would have given the share S1, and in that case the secret S prime could be the secret from the viewpoint of the first shareholder and so on. That means, just based on t shares, adversary will completely fail to uniquely reconstruct back the dealer's original polynomial and hence the dealer's original secret. That is the intuitive idea here. But it turns out that we have to perform all the above said computations over some finite field to achieve security and to avoid working over an infinite domain. So, let us try to understand first some basic facts about polynomials over a finite field. So, imagine I am given a finite field which has two operations plus and dot, and when I say that I have picked a t degree polynomial f of x over the field, I mean to say that I have picked t plus 1 coefficients from the field and my polynomial f of x is defined like this. Next, let me define what we call as the root of a polynomial over a field. So, if I have a polynomial f of x over the field, and if I pick a value x from the field, then that value x from the field will be called as the root of that polynomial if the value of the polynomial at the value little x will be 0 is 0. I stress here that all this plus operation, dot operations that I am performing when I am defining the polynomial over the field are the plus and the dot operation over the field. They are not the numeric plus and the numeric dot operation. Now, another well known fact from abstract algebra which we can use here is the following. If we are given a t degree polynomial f of x over a field, then it can have at most t roots. More specifically, if I take the case of t is equal to 1, and if I have a straight line defined over a field, then there can be at most one x value where I obtain that the value of the straight line or the straight line meets the y axis here, and this is true for any t degree polynomial over a field. And based on this theorem, we can state that if we have got two distinct t degree polynomials, say f of x polynomials and g of x polynomial over a field, then they can have at most t common points. They cannot have t plus 1 or more number of common points. So, for instance, if you have two distinct straight lines, they can intersect at most one point. They cannot intersect at 2 points, because if they intersect at 2 common points, then the two straight lines are basically the same straight line. And in general, this generalizes for any value of t. Again, I am not proving these theorems, these are some well known results from abstract algebra. And the final result which I am going to use for defining for this giving the description of Shamir sharing is the Lagrange interpolation formula here. So, what this theorem basically says is, if you are given a pair of t plus 1 x y values from the field where the x components are distinct, then there exists a unique t degree polynomial, say f of x, such that this x comma y values lie on the polynomial. That means, f of x I values would have given you the corresponding y values. And to see how exactly we can compute this polynomial f of x satisfying this t plus 1 x comma y values, let me define an ith x polynomial as follows. So, this ith polynomial is delta ix polynomial, its degree is t, because in the numerator I have t terms of the form variable x minus some xi. And the way I have defined this delta ix polynomial is that it ensures that delta I of xi is equal to 1, because if I substitute big X equal to little xi, then numerator and denominator becomes the same. On the other hand, for every value of xi different, for every value of xj different from xi, this polynomial delta I of that xj becomes 0. That means, this delta I of x1 will be 0, delta I of x2 will be 0, and in the same way delta I of xt plus 1 will be 0, because if I substitute for instance x equal to x1 here in this delta ix polynomial, then the numerator will become x1 minus x1 and hence 0. In the same way, if I substitute x equal to x2, the numerator x2 minus x2 will become 0 and so on. That means, you can consider that this delta ix polynomials are such that it survives at x equal to little xi, whereas it vanishes at all other xi values. Now, my goal is to find out that unknown polynomial f of x passing through the t plus 1 given pairs of xi y values. And I can represent that unknown polynomials in terms of this delta ix polynomials as follows. My f of x polynomial is delta 1 times x, the first delta polynomial times y1 plus second delta polynomial times y2, and like that the t plus 1th delta polynomial times the t plus 1th y value. And it is easy to see that indeed f of x1 will be y1, because for f of x1 because for x equal to x1, my delta 1 polynomial will survive and give the value 1, and 1 multiplied by y1 will be y1, whereas all the other delta polynomials will vanish off. In the same way, for x equal to x2, all my delta polynomials will vanish except the second delta polynomial, which will give the value 1, and 1 multiplied by y2 will give me y2, which satisfies my condition. So, that is a unique t degree polynomial f of x, which you can find out passing through the given t plus 1 pairs of x and y values where the x components are distinct. Now, you might be wondering that why the x components have to be distinct, because they have to be distinct to ensure that each of these delta polynomials have a denominator which is non-zero, and if the denominator is non-zero, then basically this numerator divided by denominator should be interpreted as if this numerator is multiplied by the multiplicative inverse of my denominator, because I am doing the division here, and this division should be interpreted as multiplying the numerator with the multiplicative inverse of the denominator, and the multiplicative inverse of the denominator will exist only if my denominator is non-zero. So, now let us go to the description of Shamir's secret sharing. The intuition I have already discussed. So, as part of public setup, we will be given some finite field where the size of the field be at least n, the number of shareholders, and associated with the shareholders will be n publicly known non-zero distinct x values, namely x1 to xn, which are values from the finite field. The sharing algorithm of Shamir's secret sharing is as follows. So, if the dealer has a secret value little s which it wants to share, then it picks a random polynomial over the field by choosing t random elements as the coefficient from the field, such that the constant term of the polynomial, which I call as f of x, is the secret s which dealer wants to share, right. And now the ith shareholder, namely the party pi, gets the share si, where si is nothing but the value of this polynomial picked by the dealer at x equal to xi, and that is the share for the ith party. The correctness of this secret sharing is trivial. That means, if imagine out of this n shareholders, any subset of t plus 1 shareholders come together by exchanging their shares, then they can uniquely reinterpolate back the t degree polynomial f of x using the Lagrange interpolation formula that we have discussed in the earlier slide. And to prove the privacy, we are going to prove that if we take any set of t shareholders among these n shareholders, then their shares are independent of the underlying shared secret s, because intuitively this is due to the fact that the coefficients of the polynomial which are picked by the dealer for sharing the secret are uniformly randomly chosen from the underlying field. So, let us make it more rigorous. So, let me define a set f superscript s comma t to denote the set of all t degree polynomials selected from the finite field whose constant term is the secret s. So, it turns out that the number of such polynomials of degree t whose constant term is the secret s is nothing but the size of the field raised to the power t, because the number of such polynomials is nothing but the number of candidate a values, the number of candidate a2 values, and the number of candidate at values. Now, since each of these coefficients could be randomly chosen from the field, I have the number of candidate a1 values is nothing but the number of elements in the field. In the same way, any value from the field could have taken the candidate a2 values, and hence the number of candidate a2 values is nothing but the number of values from the field, and the same is true for the tth coefficient in the polynomial. So, since each of the coefficients could be any of the values from the finite field, it turns out that I have size of the field raised to the power t number of polynomials of degree t whose constant term could be the secret s. That is the cardinality of this set f to the power s comma t. Now, I want to prove the secrecy property of Shamir secret sharing. So, without loss of generality, assume that the first t shareholders are corrupt. That means, they have seen the shares s1, s2, st, and they know that these shares are nothing but the value of some unknown f of x polynomial selected by the dealer, evaluated at x equal to x1, x equal to x2, and x equal to xt, right. So, x1, x2, xt, they are publicly known. What is not known to these shareholders, these corrupt t shareholders, is the exact value of the f of x polynomial selected by the dealer, and my goal is to show that these t shareholders are these t shares are independent of the actual secret picked by the dealer. So, to prove that, I claim here that if I take this t shares, or if I take any arbitrary set of t shares s1 to st, corresponding to those t shares, there exists a unique polynomial f of x belonging to the set f to the power s comma t, such that the shares S1 to St would have lied on that polynomial. And this is because of the fact that I can't have two different polynomials f1 of x and f2 of x from the same set f over f to the f superscript s comma t, which would have given me the same set of t shares S1 to St. Because if I have two such distinct polynomials f1 of x and f2 of x, such that f1 of x evaluated at x equal to x1 to xt would have given me s1 to st, and for the another polynomial f2 of x as well, it holds that the f2x polynomial evaluated at x equal to x1 to x equal to xt would have given me the values s1 to st. Then it implies that these two different polynomials f1 of x and f2 of x have same values at t plus 1 distinct x values, because remember the constant terms of this f1 x polynomial and f2 x polynomials is nothing but the secret s. That means the point or the value 0 comma s also satisfies both these two polynomials along with the remaining t pairs xi comma si, which is simply not possible because we have stated one of the facts that two distinct t degree polynomials can have at most t common values. So, that means there could be only one single f of x polynomial from this set f superscript s comma t, which would have given these shares S1 to St. Okay. Now, based on all these things, I claim that the shares S1 to St, which are seen by the first corrupt t shareholders or any set of t shareholders, in this example I am considering the case where the first t shareholders are corrupt. So, I claim that the shares S1 to St, they are independent of the actual secret shared by the dealer. And to prove this claim, let us consider another potential candidate secret S prime and try to argue with how much probability the shares S1 to St could be the shares of the secret S, and with how much probability the same set of t shares could be the shares for S prime. And I will show that with same probability this set of shares S1 to St could be the shares of the secret S as well as for the secret S prime. And that will prove that this set of t shares S1 to St, they are independent of the actual secret S. So, for doing that, let me introduce t plus 1 random variables here. So, I introduce the random variable S to denote the actual secret which the dealer might have used or picked for sharing, and I denote t additional random variables S sub 1 S sub t in bold notation to denote the value of the t shares which the first t shareholders who are corrupt in this analysis are going to obtain. And I want to compute the probability that what is the probability that dealer has used a secret S for sharing, given that the first t shareholders are seeing the shares little s1, little s2 and little st. And I also want to compute what is the probability that dealer has shared the secret little s prime, given that the first t shareholders are seeing the shares little s1, little s2, little st. It turns out that both these probabilities are same, namely 1 over the size of f or the size of field to the power t. This is because if dealer, the probability that the secret shared by the dealer is little s, given that the first t shares are s1 to st, implies there exists a unique polynomial say f of x which dealer has used while sharing, while invoking the Shamir secret sharing, whereas the probability that dealer has used or shared the secret s prime and that resulted in the shares s1 to st implies that dealer has used the unique polynomial g of x from the set f to the power s prime comma t during the invocation of Shamir secret sharing. But if you remember the step of Shamir secret sharing, the polynomial that was used by the dealer is randomly chosen either from the set f to the power s comma 2 or f to the power s prime comma t. That means, the probability that indeed f of x is the polynomial picked by the dealer and s1 comma s t are the resultant shares is 1 over the size of field raised to the power t, and the same holds with respect to the secret s prime. That means, from the viewpoint of the t shareholders, in this case the first t shareholders, with equal probability the shares s1 to st could have come from the secret s or they could have come from the secret s prime, and that means the adversary is completely clueless whether it is the secret s or whether it is the secret s prime which is shared, and that formally proves that Shamir secret sharing satisfies the requirement of n comma t secret sharing. So, that brings me to the end of this lecture. Just to summarize, in this lecture we introduced the problem of secret sharing, n comma t secret sharing, and we saw three constructions. We saw the construction of additive secret sharing, where the threshold is n minus 1, and then using this n comma n minus 1 secret sharing exponential number of times, we saw a solution for any n comma t secret sharing, which we call as replicated secret sharing. And finally, we saw a clever construction of n comma t secret sharing, which is a polytime solution for any value of n and t due to Shamir. Thank you.